English.
Good afternoon, everyone. Welcome to another department seminar. Today, we are very honored to have Alberto Krone-Martins here with us. Alberto graduated in physics at the Instituto de Física da USP and is master and doctor by IAG, with a double degree PhD in astrometry and astrophysics at Université de Bordeaux in France. He spaced through postdoc and staff position at the Universidade de Lisboa and Caltech, and currently he is at the University of California. He's also a long-time member of the Gaia Space Mission Data Processing and Analysis Consortium, and his work lies at the intersection between astrometry, astrophysics, computing, and engineering. Today, Alberto is going to present the talk, GraL Searching Gravitationally Lens and QSOs with Gaia Astrometry, quantum computing, and beyond. So let's start. Questions can be asked after the presentation here on YouTube or Google Meet chat. And Alberto, thank you for accepting our invitation, and you can go whenever you want.
Thank you very much, Laura. Okay, first of all, thank you very much for attending, for those who are here, for attending in person. Thank you a lot for the invitation. It's a great pleasure to be here after, I think, 7 years or like 7, 8 years now, more or less. So this is like a place and like this entire building that will live always in my heart. Thank you very much for inviting me to present at the seminar. Anyway, so today we are going to be seeing a little bit, and we're going to be talking a little bit about like things that go from astrometry to quantum computing. So, and like why we are using also quantum computing to solve some problems, especially related to machine learning problems, right? I will be very happy if by the end of this talk, so the presentation is more or less divided in 3 parts. I will be very happy if by the end of this talk, you will be able to answer why we are looking for new lensed quasars, and especially why we are using Gaia to look for new lensed quasars, right? Which is like, Gaia was created to study the Milky Way, right? Not extragalactic objects. So why we are using Gaia to look for new lensed quasars. Also how we are discovering new lensed quasars using Gaia and machine learning methods, and also the future, so where we are going, and like how this search for new lensed quasars, and also how we are profiting from those quasars to study things like the age of the universe and things like that. Anyway, so let's start with the motivation. So why? Why we are looking for new lensed quasars? So this is a very personal and perhaps, let's say, selfish reason. I just find them beautiful. It's like, it's a part of like having a wonder about the universe. Like, so you look at the universe and you want to like to appreciate its beautifulness, its vastness, and also in a certain moment you start trying to understand them, right? Because if you're just looking for beautiful things, like this is like one of the most beautiful lensed quasars that we found, in my opinion, that we called the Auriga slingshot, because it's in Auriga and it looks like a slingshot. It's just not like because they are beautiful aesthetically, but also because they help us to understand a little bit better lots of things in the universe. So lensed quasars are among one of the most useful extragalactic objects that lies around, right? And one of the reasons why they are so useful has to do with how this phenomenon appears, okay? So let's see, like very briefly, how this phenomenon appears. So essentially this is a quasar on the background, like the quasar is laying very far away. This is the Earth, so the observer, this is us. And in the middle, there is some mass, so some galaxy, for instance. The galaxy is distorting. It's not necessarily in the middle, so the position can change a little bit. But the gas distorts space-time, and then the photons that are emitted by this quasar very far away, they bend in the distorted space-time. So when they bend, the photons that arrive on Earth appear as they were coming from a different position, not directly from the position where the quasar is, but from a position distorted a little bit. And depending on the configuration and the alignment and then how the mass is distributed on the galaxy, you can see 3 images or 5 images. So normally we say 2 or 4, because the central image is deflected, so we lose information in the center. But like we normally we talk then quads or double image quasars because they form 4 or 3 images. If everything is perfectly symmetric, you're going to see what we call the Einstein ring. You're going to see a real ring because you're going to have an infinite number of images that's going to create a ring. So essentially, this is just because you're going to have like a solution that's perfectly infinite. You're going to create an infinite number of images around. Anyway, so this is how the quasar is formed, right? So the length of the quasar is formed. So why they are useful? One reason why they are useful has to do with the fact that that quasar over there is varying along the time. So it becomes brighter or fainter along the time. It's varying stochastically, right? So when it varies, so you have, if you can measure the photometric time series, so how each one of those images are varying along the time, what's going to happen? So since the alignment is not perfect, the photon path in the universe is going to be a little bit different between each one of the images, right? Since the photon path is a little bit different, you're going to see one image becoming brighter, and then only a few days or a few hours afterwards, the other image becoming brighter. So there is a time delay between the different images of the lensed quasar, right? And this time delay is extremely useful. Why? Because if you can measure, like here you're seeing like 2 time series of a real lensed quasar, so the measurement of the magnitude along the time of 2 images perhaps of that quasar, of that lensed quasar. So this image and this image. If you can measure the difference in time between the variation of one image and the other image, and if you can model, so if you can measure then this time delay, and if you can model more or less the geometric configuration of your system, so the position of the lensing galaxy with respect to the quasar, with respect to you, and the redshifts involved, if you just believe more or less in GR, general relativity, you can essentially estimate what's going to be one of the holy grails of modern astronomy, which is what we call the H0, so the Hubble constant, right? So we can infer then, so this is literally obtained by modeling, and this is just a measurement, a direct measurement. And the modeling here, it's very simple. So in theory, you just need to believe in GR. So there's nothing much more complex than this, right? And then you can infer H0, right? The problem, obviously, is that those objects are rare, right? So, and you can never model perfectly a lensed quasar. You need to have, like, to count several different lensed quasars and get to an estimated value of H0 that would fit most of your lensed quasars at the same time. So this is what we call Bayesian hierarchical modeling. Okay, why H0 is so important? So one of the biggest reasons why H0 is so important nowadays, and it has been like that for like going on and off for since Hubble time, essentially, it's because there are 2 major families of values for H0. There has always been like a big value for H0 when you measure H0 or when you infer H0 based on the local universe probes for H0, including lensed quasars. And then there are very low values for H0, like around 67, which are based on CMB data. So if you go to CMB, if you go to the early ages of the universe, you get a lower value of H0. And if you go to like all the other probes, you get a higher value of H0. And this tension is way beyond 5 sigma already, like, considering all the errors involved. What does that mean? Well, nobody knows yet. That could mean 2 different things. Either there's something fundamentally wrong in our understanding of the early ages of the universe, so there are missing ingredients to understand the early universe, and that would take the early universe H0 higher, or there are systematics involved in measurements, either in the early universe or the younger universe, or low redshift universe, that would put that H0 also, again, into lower values. Like either is one thing or the other, or again, the most interesting one is the first option. There is something missing from our understanding of the early universe, right? That means completely new physics, right? Nowadays there is essentially a race to get H naught, especially in the early, in the nearby universe, so the late universe, to lower the error bars, because the error bars for CMB data are already very low, but the error bars for our low redshift probes are very high, right? And now the race is getting those bars smaller and smaller and smaller, right? And hopefully trying to understand why there is this tension between the lower values and the late values of H naughts. Okay, so this is one of the biggest reasons. So this is the biggest reason, actually. But there is another very good reason for us to study gravitationally lensed quasars, and it has to do with what happens in this foreground galaxy. What would happen if around this galaxy you would have like other small things, like other small clumps of mass that we cannot see, but although we cannot see, they're going to distort space-time, right? So what would happen then when you add all those small clumps around the galaxies that are creating the lens? Anyone wants to say anything? What will happen with the position of those images? The positions are going to stay the same, or the positions are going to change a little bit? So their positions are going to change a little bit. So you add some mass, you distort space-time a little bit more, and then the positions change. So what happens is that when you add small clumps of dark matter that you cannot see in the lensing galaxy, but they're distorting space-time, and they are actually they are changing the positions of the images of the lensed quasar at the sub milliarc second region. So a few hundreds of microarc seconds when you talk about 10 to the 5, 10 to the 6 solar masses, halos, so those dark halos around the lensing galaxy, right? If you can measure, and especially if you can do very fine astrometry, so very precise and accurate astrometry of those positions of the lensed images of the lensed quasar, you can actually measure, or infer, not measure, you can infer the cross-section of the dark matter that's creating those small clumps. Because when you change the cross-section, you change how the number of small clumps and the amount of mass in each one of those small clumps. So this is the second reason why we have been chasing for those gravitationally lensed QSOs. The problem of all of that, so with the problem with H naught and the problem with the dark matter, actually comes to this. They are very rare. So the lensed quasars where we can measure those things, they are very rare. So essentially it took humankind about 40 years between the early predictions by Zwicky et al. And the actual confirmation of a multiple image lensed quasar. So it took 40 years more or less. And then since the first observation of a lensed quasar, we were discovering more or less one per year of the quads. Not only quads, but everything together until 2016, 2017. In 2016, 2017, everything changed. The number of lensed quasar published and discovered started to grow significantly and very quick. Why? And that's where like Gaia come, right? So Gaia actually changed completely the game in the discovery of lensed quasars. Again, most people remember Gaia as a machine to study the Milky Way, and it was created to study the Milky Way points. But it's a space satellite with a mirror that's like about almost 2 meters in the highest resolution. Gaia mirror is rectangular, so it's asymmetric. So there is a high resolution angle and a low resolution angle, 90 degrees of it, right? So in the highest resolution direction, actually, you get like a PSF that is Hubble's PSF minus 15 milliarc seconds. So it's essentially Hubble, but different from Hubble that you're pointing, or James Webb that you're going to be pointing to a few regions of the sky. Gaia is observing the entire sky. So you get everything everywhere, right? We select on board what we're going to to send to the Earth. We don't send everything. We send all the stars and everything that's more or less point-like. And we changed a little bit the parameters to also allow Gaia to send some galaxies, right? What you're seeing here is about 6.7 million galaxies. So this is a map, like in the Milky Way, there is nothing. But if you go away from the Milky Way, you see like more or less the large scale structure of the universe up to Z 0.2. Right? And what we're seeing here is 6.7 million galaxies that are going to appear in a forthcoming Gaia data release. So this is being constructed now. This is used as an input data to Gaia. Anyway, among all those extragalactic objects, Gaia is expected to observe about 2.6 thousand Lancet quasars. Nowadays, we know a few hundred Lancet quasars. But inside Gaia data, we have about 2.6 thousand Lancet quasars if you believe in lambda CDM, right? From the moment that you change a little bit the parameters, the numbers can go up or down. But if a standard lambda CDM universe, Planck universe, you get 2,600 Lancet quasars. Out of those quasars, 250 of them are going to be quads, so quadruply imaged quasars. So those are the most valuable quasars that we have, right? Because since they are quads, we can constrain the modeling better. And that actually, if you can constrain the modeling better, you don't remember the equation? Oops. Oh, wrong. Yes. So if you can constrain this part of the equation better, you can get a better H0, right? So normally, for H0 to work, you focus on quadruply imaged quasars and not in doubles. This is changing now because doubles are much harder to measure and they're much harder, to model. But essentially, historically, quads are better to obtain H0, okay? Okay, so yes. How do we use all those Gaia data? So just up to this morning, this Gaia data means 2 trillion measurements. So there are 2 trillion individual astrometric measurements of everything in the sky. So as of like a few hours ago, like I took the data like 4 hours ago, more or less. There are 2 trillion points, individual points in the sphere that you need to create methods to go in those 2 trillion points and get, okay, those 2,000 Lancet quasars, right? What we're doing to discover those things. Okay, so the first thing is, at each Gaia data release, we do a bulk download of the data. So we download everything. We don't use the Gaia archive, actually. We use the Gaia archive just to download everything. Where everything goes. So this data, people might remember, like if you look to the side of the slide, you might remember on the astronomy department, this machine. So this is the old Alpha Crucis cluster. And in the cluster, there is a node that was built by Rama in a FAPESP project, which is like a high memory node. It's a node that has 1 terabyte of RAM. So the entire Gaia data release comes to IAG and goes to the RAM directly of the machine. And we perform the search. We don't use scratch disk. We use directly the RAM. So this is faster, right? And historically, we have been using this machine. Nowadays, we are using, the machine had some problem during COVID. And then I deployed another machine at California, which is this other machine here, which is interesting. If you like computer sciences, it's not an Intel type of CPU. It's an IBM type of CPU. So everything's a little bit weird. But anyway, we can talk about those things later. It also has 1 terabyte of RAM. Anyway, in RAM, the machine starts cross-matching the Gaia catalog with other stuff. So what is other stuff? It's Catalina. Catalina is a time-resolved survey. ZTF, which is another time-resolved survey. WISE, Pan-STARRS, and anything actually that exists on the virtual observatory can be cross-matched, because we use a TAP client to do queries on remote archives and cross-match all the information that we want, right? Anyway, and then for the lens selection, so that's the data that we use. So the data actually, so the data here, you can imagine that's like it's a cross-match of several catalogs. So you can imagine that there are a lot of columns already, right? So we're talking about thousands of columns. And obviously we use many different methods to explore different subsets of those columns. There are three major families of methods. One is based on astrometry and photometric patterns that works very well for quads. So essentially we train machine learning methods to recognize the quads based on the angles between the different images, right? Then there is a method that I'm going to talk a little bit more based on time series, and especially about how ordered and how organized are the time series. And then there is another method that's based on images from ground-based surveys together with Gaia data. And then this is based on power spectra of the images, wavelet and Fourier power spectra of the images themselves. And astrometry goes everywhere, by the way, because astrometry is the most constraining factor to say this is a lens equation, right? Because you have the correct, more or less the correct angles there. Right? Anyway, and then there are many other methods, but those are the three major families that we use. Anyway, why we use those methods? So we mostly use those methods to take from the 2 billion initial Gaia sources into about 1,000 candidates. So we take the entire Gaia data release and we transform in 1,000 things. Why 1,000? It could be 10,000, it could be 100, but like the idea of this 1,000 is because 1,000 is the number of actually data that I could inspectors, people in the collaboration could inspect by eye. And this is where we trust machine learning methods. I love machine learning, I love computers. But software is just like sausage. If you know how software is done, you take a lot of care in eating it, right? Yeah. So we trust computers, they help us, but they don't replace us. So the idea is that we go from 2 billion things into 1,000 things that we inspect. And then after we inspect, we veto things, or we select some things, and we select like about 100-ish sources that normally go to telescopes, right? And then those 100 candidates, then those are the candidates that we go to telescopes to take spectra to try to confirm or not, right? And the telescopes that we mostly use, that we have been using in the past 5 years. So we started with Keck. Our first observation was actually at Keck. And then we started using Hale and Keck for north. And in the south, we have been using NTT, SOAR, and Gemini, mostly. And VLT as well. But VLT for IFU observations, essentially. And Gemini as well. And we also used a little bit of DOT and a little bit of BTA as well. Like the BTA telescope was super fun. Anyway, it was anyone has ever heard about the BTA telescope here? So the BTA telescope is a 6-meter telescope in the middle of the Caucasus Mountains. So it's a Soviet telescope. It was the biggest telescope at a certain moment. Anyway, this is a trivia. We can talk about that in the coffee break. Anyway, and then after we take the spectra, we analyze the spectra, this fits back into the system. So this enter back in the lens candidate selection. Now the machine learning methods are retrained again. And this keeps, this is a loop. This is a continuously learning loop. It's more or less like we are not trying to do artificial intelligence here. We are trying to do some sort of augmented intelligence, right? So we don't replace the human being. The human being is always here, right? And the final decision is taken by the human. The machine is there, just like we are wearing like our shoes. We can walk better, we can walk farther away, but we still walk, right? At least for now. Okay. So again, there are 3 major families of methods. As I mentioned, I'm going to just jump the first one. The first one is trivial, right? So we use supervised learning with positions, like we generate 100 million simulations of lenses. And more or less the equivalent number of non-lensed things, right? And we add all the errors that Gaia has, so we train with a biased set, right? And then we apply this model that we trained to Gaia data, and then we select candidates. So this works perfectly for quads. This fails miserably for doubles, because anything can be 2 points, right? If you have only 2 points, like you have 2 dots, you have 2 stars everywhere in the sky, right? Even 4 is already meh, but it helps a lot. But 2, it's impossible. So for doubles especially, we created the other families. The first one is based on time series. And this one's quite interesting. So the role of time series. So how we use time series to actually measure or to get a candidate for a lensed quasar. If the entire sky was resolved as Euclid is going to resolve for us in a few years, or as Gaia is resolving for us now, right? So we have like 150 milliarc seconds PSFs in the entire sky every single night, it would be easy. The thing is that this is not the case, right? So most of the time resolved surveys are ground-based surveys. So we have PSFs between 1 and 3 arc seconds. Like one of the both surveys are actually from both surveys that we use are actually from California. So CRTS and ZTF. ZTF is on Palomar. So we have PSF from Palomar. So it's 1 arc second very rare. So it's unresolved. So how do you use unresolved data to actually detect a lensed quasar? So imagine that you have a non-lensed quasar. So if you have a non-lensed quasar, you just have a random time series. It's completely stochastic, right? If you have a resolved quasar, a resolved lensed quasar, you have the same time series because the time delay is the same images, the same quasar in different parts, with the time delays between them, right? So we have this time. So if we had surveys like this, it would be detect the lenses, but we don't. So what happens? What the atmosphere is going to make with this data? The atmosphere will essentially transform all the images into a single blob, and what you're going to be seeing is the same time series. So it's the same photometric time series added on top of itself, but with a time delay. What does this create? So what happens if you compare this time series, which would be the time series for a completely normal quasar without lensing effect, with a lensed quasar that you cannot resolve, but it's a lensed quasar? What happens is that the entropy of this time series is going to be lower than the entropy of this time series. Because here you have the same information repeated after a while, again and again and again. And this is going to create an autocorrelation on top of your time series, right? So the entropy here is going to be lower. So you can actually use entropy as a good indicator for, okay, this is perhaps a lens. It will never be certain because you can have quasars that are more organized somehow, right, by nature. But if you take the general population of pure quasars that are non-lensed and the general population of lensed quasars, the entropy of the general population of lensed quasars is going to be lower than the distribution of the entropy of any quasar, right? And this is another data that we use to detect lensed quasars. So I'm not going to talk about everything, but we use entropy is the most important flag here. But we use other things, like we calculate power spectra and use power spectra of the time series and so on and so on. The problem here, again, is dimensionality, right? So you have entropies, you have power spectra, you're going to have hundreds or thousands of data columns to deal with. Now, we use machine learning methods, in this case supervised, and we know about 200 quasars. So we have 200 rows and thousands of columns. How can you train a machine learning model when you have like much more features than examples? Like you cannot. You need to find somehow some transformations or like some selection of what's the relevant data to train. And this is what we're going to talk about later, and this is where quantum computers are going to enter. And well, after you do things, We just train normal ensemble of machine learning models. The third type of data that we use is imaging. And for imaging, what we use is wavelets. So raise your hands if you heard about wavelets before. Okay, a few. Okay, so imagine then, like, raise your hand if you heard about Fourier transforms. Good, much more. Okay, good. So imagine that, like in a Fourier transform, you're going to express your signal as a summation of sinusoidal functions, right? And sinusoidal functions are infinite in time, right? They go to the infinite in both directions, right? A wavelet, you could imagine, that's like a sinusoidal function, but that damps somehow when you go away from the center of the wavelet. Like, so you have an additional parameter, right? So the wavelet's localized. So wavelet transform is localized, the Fourier transform is not localized, it goes to the infinite, right? So this is just an example of a wavelet decomposition, for instance, for an image. So suppose that you have this image of a galaxy. When you try to use wavelets to describe this image, you're going to try to break the components of this image into the different scales that you can have in the image. So you can have the coarser scale, that you have like the finer scale, that have only the very tiny fluctuations of the data. Then you're going to go to coarser and coarser and coarser and coarser parts of the data, right? You're going to become like more smooth, the more smooth components of the image. And then this is just a reminder. So what we use is more or less the equivalent of a Fourier power spectrum. So how much power do we have for each image in each scale? So how much power do we have for each image of each length or each known length? And use those power spectra to actually, as features, the entire power spectra, as features in the classification, to help the classification of lensed quasars. And why? And this is especially effective for very tight lenses. So imagine that you cannot resolve, but barely resolve a lens. You have the 2 or 4 images of the quasar, and then you have the galaxy there in the middle, right? You cannot resolve, but if you calculate the power, a lens will have a little bit more power for the red channel that's localized in the center of the image than a non-lens, right? Because you have the difference in powers, how the powers vary between a lens and just a normal quasar, or like a double quasar, or a quad. Not a quad, but normally a double quasar. So we use then wavelet and Fourier power spectra, plus a measure of the differences between the images themselves. I'm going to talk about cluster in a minute. And the reason why we use power spectra and not just the wavelet transform or the Fourier transform is because when you calculate the power spectra, so the amount of power per scale, you have what we call translational and rotational invariance. So the power, like if you take an image of my head, the power is the same, the power spectrum is the same whether my head is like that or like that or like that, right? So regardless of how your image is rotated, you have the same power spectrum. And I never understood why people don't use this in neural networks, and they keep doing data augmentation, right? So instead of doing data augmentation, you could just go to spaces where you gain translational and rotational invariance. Anyway, and this is very important because you're not inventing data, right? You're just going and moving to spaces where you can profit from invariances to train your models. And this is what we're doing here. In any case, we calculate power spectra for each one of the bands. And even from the subtraction of bands, like G, R, I, Z, Y, and G minus R minus I. We calculate all those things, and we have power spectra. Now we are talking about tens of thousands of columns, if you just concatenate one power spectra after the other. Which are the relevant parts of the power spectra that you need to use, right? We don't know yet. So this is, again, we're going to talk in a few minutes. After we get the features, then we move into simple standard machine learning models that we train from one side. Here we use supervised methods like XGBoost, and non-supervised, unsupervised, very simple clustering, hierarchical clustering methods as well. Okay, so those are more or less the methods that we have been using. So you can always ask, I don't know, it's fun. Like, it's a very fun experiment in computer sciences, in computing, in engineering, to build all those things. Are they actually useful for something? Well, we have been discovering many lenses because of those methods, actually. And this is the first one that we discovered. So this is 1131 minus 4419. So what we are seeing here are those four dots that were Gaia. Those are the Gaia measurements that were published in year 2. So when we got to those measurements, we ran the machine learning methods. This was selected. We ran the modeling. We got a small model that fitted the lens perfectly. We decided it was good enough, and this we were talking about 3 hours after the actual data release. We were up, I don't know, it was 3 or 4 a.m. At Caltech, and we are there like crazy, using UV100 here at IAG to get the candidates. And then we saw this lens, and this is a good enough candidate for us to actually ask and point KEK to it. And just like after 2 days, we were pointing KEK to here. Do you remember like your observational astronomy classes? Would you point KEK into minus 44 declination? So KEK was essentially looking like Hermes of 2, and then the actuators were like, hold the mirror. And we are asking never to do this again. But anyway, the observer was very good. He was a very experienced observer, Daniel Stern. Anyway, he was brave enough to point to this. We pointed KEK to this, took the spectra of the combination of those images and those images, and those are the spectrum. So if you see the spectra here, you're going to see all the correct emission lines in the correct places, just confirming. Like, we were so happy when we saw this lens. Great. This was our first lens, by the way. After this lens, we have been, it was not only the first lens, it was a quad already, right? After our first quad, we started discovering many more quads, including that same night. This was also discovered that same night, which was also published by another group. That's why there's another name down there. And so far, using those methods, we discovered a total of 20 quads, like 16, 17 completely out of doubt. And then there's a few that like we have modeling confirmation, but not fully reduced data and so on, right? But it's around 20 quads alone. And also the doubles, right? So those are examples of double image quasars that we discovered. Those 8, essentially because of the entropy method that I just described a few minutes ago, right? The total number of doubles, it's around 73 doubles, more or less, that we have nowadays, right? This includes also some objects that are probably not lenses, like this one. This one is very likely a binary quasar and not a lens, because like no matter how much we try to detect the lens galaxy, we cannot see the galaxy. So either there is something very weird in the universe, or it's just a double quasar, right? And time series can actually prove if it's either one hypothesis or the other, because like if it's a binary quasar, the time series is going to be different. If it's a lens that's created by a completely dark object, then the time series are going to be also exactly the same, right? It's very unlikely to happen. It's probably not going to happen. Anyway, among all the lenses, there is one that was very fun, that actually Hubble discovered with Christine in NTT, which is this one. This one, the name is the dragon's kite, because it looks like a kite, right? So the fun thing about this one, it's because it's ginormous, it's gigantic. For a lensed quasar to have like, it's 11 arc seconds, 10, 11 arc seconds from one side to the other, right? So it's a gigantic lens. How is it possible that for, I don't know, 40 years it was not discovered, right? And it's even more interesting to see that this one, if you go to the 1985 Palomar plates, you can already see more the lens there, right? Including the galaxy. You even see the galaxy from data from 1985. The method was missing, but the data was already there to be like, we're just waiting please discover me. Write some software to discover me, right? And this is what we end up doing. Which is even more striking. This is 1985, right? You can go back to 1954. And okay, this is far-fetched, but there is already the 4 dots there. The data was also there already somehow. And it would be very fun if it was discovered by then, because this is actually before quasars were discovered, essentially, right? However, the lensing prediction was already there, so this would make Einstein even happier than he already was, perhaps. And certainly, this would probably make Zwicky a little bit less grumpy than what he was, right? Because he predicted that this should happen. Anyway, nowadays with those lenses, what we are doing, right? We have been conducting several follow-ups of the lenses, including to study H0 and dark matter, but also going to higher energies observations. So this is just an example of a lens, a quad, one of our quads, that was observed during the pandemic, actually, with VLA, and now we also have now VLBI data. Why VLBI? Because we want to arrive and to study the structure at the 1 milliarc second resolutions to try to detect any perturbations about 10 to the 5 to 10 to the 6 solar masses. So small, very small halos in the lensing galaxy creating that lens. Not only that, but there is a few of them that are now going to VLBI. And obviously, they are also being followed up by HSC. There's a nice observation of that our first lens from HSC, where you can see the arcs like already. And this was kindly provided by Fred Kurba. And we are also observing again, like using XMM, all of the lenses to see like what is the characteristics of the black holes of the quasar, like that's being fed, right? And we have been also, like this one essentially is one of the most energetic objects at that redshift range, by the way. Anyway, so this is what we have been doing so far. But one of the biggest problems that we had, and that we still have, we studied several different strategies to solve that problem, is the dimensionality, right? So we are using thousands to tens of thousands of dimensions, but we only have 200 lenses, more or less, to train, right? So we have a very small number of data points to train any method. So how do we solve this? So essentially, the question is, given a very large space, very high dimensional space, how you can find the best subspace to solve your classification problem, right? So instead of going to mathematics, let's try to build some intuition first. So imagine that you have those points. You want to classify the blue points and the red points, right? You have 2 dimensions, but 2 dimensions is too much for our brains. Like imagine that the 2 dimensions here are our 10,000 dimensions. So how would you solve the classification? How would you select what to use, right? So if you only had the capabilities to study 1 dimension, you can only see 1 dimension, right? So you are going to see the data in the X or the Y projection of that very high dimensional space, right? You're not seeing the 2-dimensional points, you're just seeing the projections, right? So you can only have, you need to choose 1. Either these distributions or these distributions to split the blue and the red points. Which dimension would you choose, X or Y? X, right? Most reasonable people would choose X, at least in this case. Why? Because what your brain is trying to do is to maximize distances, right? You want to maximize distances. Can you give an estimate of what is the maximum distance between your collection of points? There is a good mathematical distance to actually give a number to this. And this is what we call the Wasserstein distance. So the Wasserstein distance is essentially, in very layman terms, is how difficult it is to transform one probability distribution function into another probability distribution function. So computer scientists like the word Earth mover distance. So imagine that you have a pile of dust, or Earth, that needs to move from one place to another, right? So the harder it is to move the spy of dust, the larger the distance, right? So the Wasserstein distance is essentially this. So it's just describing how hard it is to transform this into this, right? So if you can calculate Wasserstein distances in one dimension, you can say, okay, x is better because the Wasserstein distance, the Wasserstein distance in x is going to be much higher than the Wasserstein distance in the y projection. So choose x to do your whatever classification, to solve your classification problem. So if our problem was one-dimensional, then there wouldn't be, like, the problem would be solved. You can just write this now in a more mathematical way. You want to minimize some function, and this function is just some term that depends on the time multiplied by a binary variable. The binary is 0 or 1. 0, you don't select the variable. 1, you select the variable. And then you just try to optimize this, right? This is solved. You can do this. This is trivial. But you're not solving completely the problem because you're just working in one projection. Imagine that your data is like this. If your data is like this, regardless of you choosing y or x, you're not going to solve the problem, right? All the projections are equally bad, essentially. But if you go to the 2 dimensions, they separate very easily. They split very easily, right? So what you can do, essentially, now that you know Wasserstein distances, you can just write Wasserstein distance in higher dimensions. And you can move into a higher dimension. Now we change our simple equation that was like that. You add another term. This other term now is another thing that depends on Wasserstein distance, but now 2-dimensional Wasserstein distances and 2 binary variables. If you select both dimensions, they are both equal to 1. And then you have that term that's going to be different from 0. If one of them is not selected, then the entire term goes to 0, right? Now you just need to solve this problem. And you know how to select the best dimensions to solve your classification problem. So the best subspace up to a very high number of dimensions. Because now you're connecting together all the dimensions. You transform your problem into a big graph, right? Very easy to solve, right? You just need to select zeros or ones. The problem is that this is a terribly hard problem to solve, actually. It was very easy to write the equation, but solving this equation is essentially like, we don't know how to solve it, essentially. It belongs to a class of mathematical problems called NP-hard, which are among the hardest problems that we have in computer sciences. So we don't know how to solve it exactly. There are a lot of heuristics to solve it. One way to solve it is to use simulated annealing. But like, if your number of dimensions is high, you will need to go to a supercomputer to solve it. And this is what we have been doing recently. We have been using a supercomputer called the Expanse, which is in San Diego. It's a 5 petaflop machine. Anyway, and we are solving this using simulated annealing. This is option 1, just brute force it. If you have enough computing power, you can solve more or less up to 10,000, 15,000 dimensions, more or less. A better way is to try to remember our quantum physics classes. So if you look to this, if you remember ferromagnetism, if you remember Ising models, this looks like a lot like the Hamiltonian of like an Ising model, right? Like you have the spins. If you think that this is a spin, and this x is a spin, and instead of being 0 or 1, it's +1 and -1, so you have a spin up or a spin down. And those are like spins of nearby and coupled particles. You're essentially talking about like the same mathematical problem. Like here you have a minus, here you have a me, you move this inside, and this h becomes this q. Like you can manipulate a little bit and transform this problem into what we call, mathematically they're completely equivalent. So what we call the quadratic unconstrained binary optimization is equivalent to an Ising model. And this is what this type of computer here, which is what we call quantum annealer, was created to solve. So this quantum computer, this type of quantum computers, they were created to solve, to find the state of minimum energy of those Hamiltonians. So if you can transform this into this, we can just put the entire thing into a quantum annealer and get the state of minimum energy of this, which is exactly what we're looking for, right? And then you select, so I spin up means, yes, you need to select that dimension. I spin down means don't select that dimension, right? So that's essentially what we have been doing. And this was the first lens that was discovered using this technique. You can see perhaps that there is a messy image here, but this messy image, there are two Gaia detections, up and down. This is more or less 1 arcsecond, by the way. Yeah, this is 1 arcsecond. And there is some red emission laying around here, which is the galaxy, like the lensing galaxy is there also. After pointing back and getting the spectra, we confirmed that this was a lens. And these were actually the 9 first doubly imaged lenses that were discovered using this technique. Like this is just a few more examples. One thing that's very interesting is that you can see, like in some images, that there is difference in colors. And the difference in colors is differential reddening. You can have like photons that are passing through in one of the directions. They're crossing some absorber in the middle of the way. So they become a little bit redder. Or they're crossing a part of the lensing galaxy, and they become a little bit redder as well. Anyway, we have been then, like those were the doubles discovered by quantum annealing, and those were most of the lenses that we have been discovering so far in the past 5 years. So those are the 16 quads. There are around 20 by now, and these are 54 doubles. There are 70-ish by now that we discovered. And now what we're doing, beyond the observations, we are also developing software to get from those lenses and time delays data into H0, and also to study the dark matter distribution around the lensing galaxies. I think that that's it. So on behalf of this nice collaboration, this is not work that I've been doing all on my own. This is a big collaboration. It's called GraL. You can see, you can recognize some people, including people who are in the auditorium, like Rama and Pedro, and also other people around the world. I would like to thank you a lot for your patience. Thank you.
Thank you, Alberto.
Sorry, I almost forgot. So 40 days from now, by the way, this is just some marketing, but 40 days from now, you're going to get what we call the Gaia focused product release. So this is like a mini Gaia data release, where we're going to get some data for a specific type of sources that the community can use to explore for whatever reason, right? And one of those data that you're going to get is around not all quasars that exist in the Gaia catalog, but around a large number of quasars. I cannot tell you how many yet. You're going to get all the Gaia detections so far, right? Like if like in a lensed quasar, or around a quasar, there are 300 measurements, you're going to have to get those 300 individual measurements, right? So you can use them for whatever you wish. And this is going to be public in 40 days, more or less 40 days. Thank you. Sorry.
Okay.
So, now, yes.
So let's start with the questions. We have
Congratulations, Alberto. Fantastic work to you and the collaborators. I have many doubts, but let's try to simplify. The first one, what about using PCA to do the data compression?
Well, yes, good question. That's perfect. We actually use PCA. When we do the dimensionality selection, we don't do the dimensionality selection on the raw data only. In several cases, we do a PCA first, and we also do, for instance, power spectra. PCA makes no sense for a power spectra. We do a non-negative matrix factorization because like power spectra needs to be positive, right? So we use correct, like appropriate actually transformations to profit from the data. But we also do PCA. But even when you're doing PCA, how many components are you going to use? You don't know. You threshold like, it's not because the variance is bigger that they are better for like classification. Perhaps a lower component that has lower variance for classifying that type of object is going to be very good. If you just threshold the PCs, you may throw away important information. So we do the PCA, and after we do the selection over the components.
Okay, understand your point. May I? Another question. In order to do H0 from this data, you need to have a time series. And how are you going to obtain that?
Good. So there are time series. So there are collaborators measuring time series. Like I can even show a very briefly like. So this time series from VST, for instance, that are being measured by Fred Kuba. There are people measuring time series, and all those time series are going to become public as well. Gaia itself measures time series. People forget about this, but each Gaia detection is actually composed by multiple, each Gaia source is composed by, on average, depending on the position of the sky, from 40 to 100 points for the nominal mission. For the extended mission, it's more, right? Mm. So you have points, like space quality points, for each one of the images. 40 points, 60 points for H0 is bad, for one lens. But now imagine that you have 2,000 lenses, and that H0 should be the same for all those 2,000 lenses. So you build a hierarchical model to solve this, right? And this is one way to do this. So actually, measuring, mixing unresolved data and Gaia resolved data. Unresolved data we have a lot. ZTF and LSSC is going to produce a lot of unresolved data. Mm-hmm. But you have constraints from Gaia that are resolved, right? So anyway, this is another PhD. So this is actually one PhD and a half, probably.
Okay. May I? The last one. I am interested in quantum machine learning, so I have been reading some papers on this issue, but as far as I know, we are not at the stage where quantum is making any significant difference in general. I wonder if this work you are presenting is different from this trend that I'm seeing.
That's a very good question. Quantum machine learning. So quantum computers are nowadays essentially almost useless for practical purposes. Almost. There is a very small specific type of problem where they are useful. And that type of problem is actually trying to get, if your problem can be mapped into this equation, it's useful. But it's also it's not like you could not solve this going to a supercomputer and brute forcing it. Mm-hmm. You can. And that's what we are doing now. And the reason why we are doing now, we are moving from the quantum computer to the to a supercomputer. It's because I can talk this. So D-Wave, which is the company that produces the quantum annealers, the only machine that you can the only quantum computer that you can actually use for something useful nowadays is the D-Wave annealer, point, which is to optimize that Hamiltonian. And you can get 5,000 qubits. Again, you can select perhaps 5,000 dimensions if they are loosely coupled together. If they are fully coupled, then you cannot get 5,000 because you need to entangle different qubits to transform those qubits into a single qubit, and then you lose very quickly the number of available qubits that you have. But anyway, the problem is we could use the D-Wave computer through Amazon. We could rent through the Amazon cloud. And it was relatively cheap for us to pay. Nowadays, D-Wave only sells, either you access it and you buy a 1-year package that costs $70,000 per year, or you don't access it. So most people stop accessing it, right? Mm-hmm. So we stopped using them at that time, right? The thing is that after you select the dimensions, and this is why most of our lenses nowadays, they are actually discovered, most of the new lenses are actually discovered using the quantum selected features. So they are quantum discoveries because the features were selected quantum in a quantum way, right? But anyway, we cannot use them as we used before. But again, quantum annealers are useful for practical purposes nowadays. Quantum computers, especially gate-based quantum computers, are useful for research, but not practical, not applied research. Astronomy is applied research in this case for CS, right? But actually, for toy cases in CS only.
Okay.
CS is computer science, by the way.
Thank you.
Thank you.
Hi, Alberto. Thank you for your talk. It was really nice.
Thank you.
And I have perhaps a naive question, but you are looking through the galaxy, so there are a lot of stars in the way. Is there a lot of false positives when you are looking for these lensed and double quasars?
Perfect question. For quads, the false positives are now much lower already because like quads are easier to actually get. Like for doubles, the false positives are higher. But there is one thing that's good. Like if you like we use Gaia. This is especially important for doubles. We use Gaia data, but a lot of other data, right? There's Ys there. And actually Gaia minus Ys makes a perfect combination to get, okay, this is a galactic object, and this is an extragalactic object. So the Gaia minus Y scholars, especially G minus W2, they are very good, they pose very good constraints to select extragalactic objects, right? Or very red galaxy objects. I think that I have, yeah. Another thing that we normally do is we start from a catalog of all the things that somebody already said that perhaps was a quasar. So we have a large compilation with 24 million sources that can be quasars. And we look around those as like the highest priority sources, right? And if you just look for that, you already got rid of a lot of the Milky Way, right? So, yeah.
Okay. Thank you.
Alberto, thanks for your talk. My question here has to do with the science of finding the Hubble constant. So when you use time delays, I think the biggest source of systematic errors will be the model of the lens.
Yes.
Especially the degeneracies in the modeling, the fact that there is contribution that comes from outside the main lens, external shear and things like that. And there is this look for a golden lens which we can model perfectly without the need of any shear from external sources. So how you guys are doing the modeling? How are you finding those things?
Perfect question. Thanks, Eduardo. So we're not looking for a golden lens to begin with. We already started from the assumption that no lens will be good to get an H0. No single lens will be good to get an H0. And the other assumption that we're doing is that if you have a large enough number of lenses, and if they are all modeled together, the H0, so if you don't assume that there is an H0 variation on the sky, so the universe is homogeneous and isotropic, and wherever you see, you're going to get the same H0, then regardless of where the lens is, you should get the same H0, right? So they should be modeled at the same time. They shouldn't be modeled independently. Even the modeling of the lens is it's not going to be done. So this is a PhD thesis that a student is starting now. And there's another, even the modeling of the lens is not independent. All the lenses should be modeled at the same time, sharing one single value of H0. The other thing is that, so we started doing this for quads. For the quads, like most of the quads that we discovered and that we are going to be using for the H0 modeling, they got either James Webb time, or they got VLBI observation, or normally end, and also IFU data, right? So we had proposals at VLT for Muse, like in very large field, essentially to get all the galaxies that are around that could add an external shear to the individual source as well. So again, modeling is terribly hard in this case, right? So the person who is responsible for the modeling of the lens is Dominique Sloos, who's in Belgium. And like the paper that is being submitted, it doesn't include modeling, but there's a paper that we submitted recently. That's the paper with the VLA observations. It's starting already to just pave the way to do this, right? So we are at 300 mass observations in radio, also to check if there is anything around that could add any shear terms for the quads, right? For the doubles, it's a completely different history. The doubles are going to be a mess, and we don't know yet how we're going to approach that part. But the most important thing is that H0 should be the same for all the lenses,
Yeah.
and the modeling cannot be independent.
But the only thing that is just not a thing of adding system, because it's not a statistical. They're systematical problems. So
yeah, but again,
of course, having more is better always, but it's not just that, like stacking
of course.
hundreds and hundreds, but
that's the thing. That's why you cannot measure different H0s and then average out the H0s together. That's impossible.
It's not that different. Doing individual modeling and averaging the H0s and doing the hierarchical modeling is not completely different things. I agree, it's much nicer to do the way you do, but it's not completely different. And doesn't get rid of systematic issues like the external contributions. Of
and
course,
microlensing.
The study of individual case by case using larger fields, of course, that's the way to do.
Yeah.
And but my experience with those things that when you are in a field with a cluster, with a group, or with other galaxies, the uncertainties on the modeling kind of kills it.
Yeah, essentially. This lens is beautiful.
Yeah, but
this lens is useless.
But given this Einstein radius, of course there is external shear.
And it has a very strong external shear, and this is a cluster.
Yeah.
So it's an 11 second.
For your purposes,
it's useless.
Not. Yeah.
Yeah. But this lens is useful. This lens is useful. This lens is useful. Like this has two objects there. But anyway, yeah.
Great. Thank you.
Thank you.
Well, I think
I have a question myself, and maybe it's a silly question, but
no.
First I want to thank you for the excellent talk, and second I was wondering, if you have you can run simulations to compensate the lack of candidates you said you have.
Mm-hmm.
You can. What are the problems involved? Can you comment on that?
Good. So. So why we are not, so the question is essentially why we are not just simulating lenses to actually increase our data sets of possible lens-like objects and then train the models on the simulations, right? So when you start doing that, you assume that you already know everything that you need to know about the lenses, right? Which is a problem, right, to begin with, because you cannot simulate everything that exists in the universe, right? And the other things, like if you would be just simulating things, let me just show one example of where this would be a problem, probably. So this good example here. This is a lens that if we were just training simulations and using a simulated machine learning model to select, would not be selected. Because this is a very weird lens. Because the difference is super strong. There is a gigantic absorber in front of one of the images. And unless you could simulate a perfect universe with all the possible scenarios of everything that could happen, if you can do that, then you can train your machine learning model and sleep well. If you're not doing that, you're biasing your selection because you're just selecting what you believe to be a lens beforehand, right?
Okay, thank you.
we have, I think, Beth has a question.
There was a question over there as well, but okay.
She's waiting.
Alberto, may I ask? Or...
Yes. Hello, Beth.
Tudo bem? Okay, Alberto. A great talk as always. You know, you always bring some very interesting new stuff, and definitely this is very interesting. So, you know, you have had a lot of questions on machine learning techniques, and I have one, but first of all, I would like to make a question regarding, you know, science issues. So, what is the redshifting interval that you are able to catch the lensing the objects?
Okay. So far, like what is the? I think that's the. Do you remember, Pedro? 5, 6, I think. So yeah. 5 around. I think that the farthest one is around 5 and something, redshift
Right.
5 and something. Yeah.
Right. And how many of those objects are really double? Because you said said, okay, this is definitely a real double quasar, right? But then after using the Hamiltonian technique, you also got a few doubles. So how many of them are really physical double objects or lensed ones?
Okay, so how many are lenses that are doubly imaged, so lenses with two images, or how many are double quasars, like that, just two quasars that are nearby, right?
Just a few.
That's a good question. If I had to guess, because we don't have that number firmly yet, because even the actual number of lenses is still varying a little bit, because a lot of them are actually mountain confirmations. We don't have the ground yet confirmation after final data reduction. But I would say that there are some very obvious ones, like the very obvious cases of doubles probably would be around 35, 40, the very obvious ones, right? Where we already saw the lensing galaxy, we have the redshifts, we have the redshift of the lensing galaxy, we have the redshift of the quasar as well, because we can see the absorption lines in the spectrum, right? So that would be 35, 40, more or less, right? And everything else is still up to confirmation, right? So yeah.
So 35 are real physical ones.
No, they are lenses.
Okay.
Not double quasars. And then the rest can be either a double quasar or a doubly imaged lens, so a lens where you see two images, right?
Right. Okay.
Well, the only way to actually confirm if it's a lens or not is to get the galaxy, right? Until you don't see the galaxy, it could be a double quasar, right?
Right. So these are, let's say, this is the confirmed ones are around 35.
Probably.
Is that what? Okay. Yeah, so it's a pretty good determination. I mean, to have out of a sample, out of this sample, to have the possibility of physical doubles. It's also interesting physically from the point of view. Real binary quasars, or you know. Yeah. So, and also this might be expected larger redshifts. That's why I asked you what was the redshift range that you got this one. Can I make a question regarding the machine learning techniques that you are using?
Yeah, of course.
Okay. The Hamiltonian, it's the quantum mechanics technique using the Hamiltonian. It's the second talk using this method that I see in less than 1 month. So it's interesting because the other talk was related to variability, to light curves studies. So it's very interesting because it shows that it has a trend for being powerful and being very useful in the next few years to apply it. So, but then you said that you decided to use this one in order to improve your sample to help with to improve your data to help with the machine learning technique. So, right?
To select what are the features that are the most relevant ones, essentially.
Right. So this is, let's say, an additional technique that you can use with the others, not something that you can use either this one or what we were using before.
Yeah,
right?
Exactly. And this can be used, and this is actually being used, for instance, to select what are the stocks that you should invest as well, right? So from the moment that you need to select a subset of a R set, you can use this type of technique, right? So it's essentially a feature selection, a way to do feature selection, right?
Yeah, because we are using these, machine learning techniques, AI techniques to build spectra at high energies, non-thermal spectra. And sometimes, you know, we get one technique, okay, it's okay, it's fine, and it's hard to decide which one is going to be better for a specific problem. So that's why I'm asking if you, at the end, you are going to choose one of them, or you are going to keep using the different ones.
Yeah, we are going to keep using all of them. So the features that we are using, that we are going to be using in the foreseeable future, are the features that we selected already using the quantum annealer, right? But after, like, that was for the feature selection, but the techniques behind, so everything that happens before and after, we're going to keep using all of them. It's not going to be a selection. We're just going to use XGBoost or like things like that, right? So, and we are actually adding more and more techniques all the time, right? So we started using also a spatial type of semi-supervised variation autoencoder as well, and stuff like that. So neural networks are a little bit worse than what we have been using so far, because neural networks, they do very well in the regime where you have a lot of data to train. And they do very poorly when in the problems like ours, where you have 200 points to train, right? Yeah, so that's why so far neural nets, I think that we had only 2 or 3 of those lenses were discovered due to some neural net technique. Most of the other things are tree-based methods, especially XGBoost.
Right. Yes, it's a good get. I mean, it's nice to know, you know, what empirically,
yeah.
which is the best one. That. Ok, Alberto, muito bacana, muito legal.
Obrigado, Beth.
Daqui a pouco eu desço aí para dizer oi.
Tá bom.
Eu estou na minha sala.
Tá bom. Essa vida moderna.
É, pois é.
Thank you for the talk. I just didn't quite understand something you said at the end of the presentation about the different colors at the QSO images. Can you repeat it, please?
Those here, right?
Yeah.
So, for instance, when you have a lens, do I have the model? Yeah. Well, do you remember the diagram? So you have a galaxy, then you have the background quasar, then it deflects the photons, and then you have the multiple images. So the space is bent. It doesn't depend on what's the color of the light, right? From the moment that you have the photon is going to follow more or less the same path. And then, so the lens is what we call achromatic. So you should have the same color, exactly the same color in each one of the images, if it's a lens, right? The problem is that there's a lot of stuff between. So in the path in the universe that the photon is going, there's a lot of stuff that this photon is going to be crossing, right? Those photons are going to be crossing. And in the end, you can have differential reddening, because like the photons that are creating this image, they are crossing a galaxy that can be the lens in galaxies or anything else, right? And then they're going to become redder, right? So unless you can simulate everything that could happen in the universe, you're not going to have a good machine learning model. Or you're going to have a machine learning model that can select any two things, like any stars, like 2 stars of different colors, right? So, and that's why, just to complement the other question, like we cannot simulate, and like you can always simulate, but it's not going to be like probably a very good model, because, well, you're always going to be biasing the lenses that you're selecting because you are biasing the simulation, right?
Thank you.
Thank you.
We have any more questions here?
First of all, nice, good talk. I really love it. And my question is about, you said you asked for timing many telescopes, one of which is James Webb, right?
Yes, I didn't ask it for the James Webb time. The James Webb time was a proposal by Anna Nirenberg.
Yeah, my question is, what specific problem or type of object you wanted to observe and study? Because the entire project is such a systematic thing that what specific object you really needed to see with James Webb?
Okay, so there are a few objects that were selected for James Webb. And actually, the James Webb program was created to study the subclumps, like very small clumps of dark matter in the lensing galaxies, right? Using a technique that actually tries to study astrometry and photometry, but in very narrow and very well-specified regions of the spectrum, right? So essentially, James Webb was, sorry, I'm not going to be. It was like the James Webb proposal is very similar in some sense, to the VLBI proposal that we have. Like it's focused on the study of around 10 to the 6 solar masses dark matter clumps that are mostly dark, right? And like the astrometric and photometric deflections created by those subclamps.
Got it, thanks.
The VLBI proposals are also focused on that. And one of the things is that to actually get it seems that H0 and the dark matter studies, they are independent, but they are not. To actually get a good H0, especially an H0 below 1% in error, you need, as Eduardo mentioned, a very good model, a very well-constrained model of the lens. And that's why we have like the HSE, the James Webb, and the VLBI, and the VLA proposals as well, to actually get all those lenses very well measured and very well systematized, and actually get 10 to the 6, perhaps 10 to 5.5 solar masses, dark matter clumps also around it.
Okay, I think this. Thanks, Alberto, again.
Thank you. Thank you very much.
And Richard, you can stop the transmission, please. And we have something similar to a coffee break outside.